In a network of simple spinors that are coupled together, the coupling is really mediated or regulated via the network, and the underlying network is what is really behind certain features. What do I mean by that? Well, instead of the linear coupling that we've just looked at, let us turn to a cyclic coupling. And that means that you can think about our oscillators, our spinors, as being arranged around a circle. And then, indexing properly, we have n different phases on these n oscillators or spinors, phi1, phi2, phi3, all the way up through phi k being influenced by the guy before it, phi k minus 1, and the guy after it, phi k plus 1. This goes all the way up until phi n. Now, if we write down the system, it's the same as it was with linear coupling. The derivative of phi sub k with respect to time is going to be epsilon times sine phi sub k minus 1 minus 2 sine phi sub k plus sine phi sub k plus 1, where this is all using cyclic indexing. That is indexing mod n. So within the system, if, say, you're looking at the derivative of phi sub n, it's going to call for the sine of phi n plus 1. Well, phi n plus 1 by cyclic indexing is really the same thing as phi 1. Likewise, when you're looking at the evolution of phi 1, it's going to look one step back for phi 0. That's really the same thing as phi sub n. Why? Because everything is coupled together in a cycle. It's as if two ends of a linear coupling are glued together with a link. Okay, now this system of n equations on our different phases has an equilibrium at the origin. As you can clearly see, this is the synchronized state where all of the oscillators are moving, all the spinors are moving in sync, and all the phases vanish. Now, what matters, of course, is the linearization of this system at the origin. We're going to get a matrix that looks just like the linear coupling case. We're going to have negative 2 epsilon along the diagonal, constant along the diagonal. On the superdiagonal and on the subdiagonal, we have constants epsilon. You can read that right off the system. Everywhere else in this matrix is going to be a 0. Except the upper right and the lower left corner, which have an epsilon term because of that cyclic nature of the coupling. That's the only difference in the matrix between the linear and the cyclic coupling. Now, it might not seem like a big difference, but it kind of is, because this is what is called a circulant matrix. Very interesting. You may not have seen these before. I'm going to skip straight to the facts. The eigenvalues for this matrix are indexed by j, going this time from 0 to n minus 1. There are a total of n eigenvalues. Lambda j is equal to 2 epsilon times negative 1 plus cosine of 2 pi j over n. Now, that may seem just like what we had before, but it's a little bit different. If we visualize these eigenvalues, what you can do in the complex plane is draw a circle about the point negative 2 epsilon, make that circle of radius 2 epsilon, and then put n equally spaced points along that circle, with one of them, lambda 0, being at 0. This system has a 0 eigenvalue. Now, all of the other eigenvalues are real as well, and you can get them from the horizontal positions of these endpoints distributed equally over the circle. So those are the eigenvalues. That is the spectrum of the linearization at the origin, if you like. Now, what does this 0 eigenvalue mean? Well, it means that the synchronized state is not inevitable. We've got one eigenvalue that does not have a negative real part. So we don't have full stability. But most of the eigenvalues are negative and real, which means, roughly speaking, most of the time you are going to synchronize, and if you do, then you do so at a particular rate, a rate given by the largest non-zero eigenvalue. And you can take that value, that 2 epsilon times -1 plus cosine 2 pi over n. You could do a little bit of asymptotics on that as n goes to infinity. I'll let you do that. The real question that I want to get at is, what does it mean that we have this 0 eigenvalue? What it means is that our system does not necessarily have to synchronize. There are long-term solutions to this system that do not involve a convergence to 0. This is very, very closely related to the topology of this ring. This underlying network has a cycle. That cycle is detected by this 0 eigenvalue, and indeed, one can have situations where there are waves that move along this circle. That is very cool, and that, too, is all about eigenvalues.